In this lecture, we will look at some examples further for momentum conservation macroscopic balancage. So, the first example we looked at when we were talking about mass conservation, we looked at the problem where we calculated the volumetric flow rate, which is V dot dA through this plane. Now, we can calculate momentum flow per unit. If we put rho into this, then that will become momentum flow. So, we will be calculating the integral, this integral, because most of the time what we will be looking at is an incompressible flow. So, rho will be simply multiplied to this integral. So, what we want to see is how to calculate this integral or how to calculate momentum flow. We have the plane. So, as earlier we will not do it in detail, but we will take a small plane on this area dl dy and then look at its projection and find the area vector dA. So, which we can write dy dz I plus dx dy k. For further details, you can go back to the example that we did in the mass conservation lecture. So, to relate, because we have dy dx dz, we will x y z need to be related, and for that we will write the equation of plane which have intercepts a, b, c on x, y and z axis, and when we do that we will get the equation of plane. Now, we will substitute these values here. So, v is x I plus y j and then we have v dot dA dot product. So, we will take the dot product x I plus y j dot dy dz I plus dx dy k. When we take the dot product of these two, because I dot I is equal to 1, j dot k, j and k are normal. So, that will become 0 and j and I are normal. So, j dot I will be 0, j dot k again will be 0. So, we will have only one term which will be I dot I. Okay. So, we will have this part within the bracket, it will reduce to x dy dz and I dot I is equal to 1, and the first bracket x I plus y j remains same. So, remember the difference from mass conservation, there it was only v dot dA. So, it was a scalar quantity, but now we have this scalar quantity v dot dA or volumetric flow rate multiplied by v, which is a vector. So, this is a vector quantity and we have to integrate it over the area of this plane. So, if you look at the limits, integral y is equal to 0 to 5 and integral z is equal to 0 to 3, as we can see from here. So, we can do the integration, we can take this inside x square dy dz I plus x y dy z dz z. Now, when we substitute the values, and because we are doing we have the limits y to z and we are doing integration with respect to y and z. So, this x needs to be written in both the places in terms of y and z, and that is where we can use the equation of plane. So, we can write x is equal to 4 into 1 minus z by 3, and when we substitute and integrate, we will get the answer in this form. We will get 80I plus 75j. So, I will leave it to you to do the little bit of algebra and calculus and find out the answer. Okay. Let us look at the next problem, which is force on a plate by a jet. So, if you are holding a plate, for example, or if a jet hits say from a water hose, the water hits at your palm, what is the force experienced by your palm, or force experienced by a plate? That is what the problem is about. So, this is an schematic of the problem, that water from a stationary nozzle, it strikes a flat plate. So, this is the flat plate and the water jet hits this plate. So, when it hits the plate, it is in such a manner that it distributes symmetrically on the two sides. The plate is vertical, okay, and we choose the coordinate system such that the jet is along the x direction and the direction normal to it is y direction. So, it is a two dimensional problem, we can say or we can assume the problem to be two dimensional. Now, we have been given the velocity. So, the jet comes with a velocity u, and the area of this nozzle from which the jet comes out. So, the jet area is A. Of course, the intrinsic assumption here is that the nozzle area and jet area both are equal, and we assume that the water stream is directed normal to the plate. So, it is normal to the plate. Now, what we need to find out is the horizontal force that is required to hold the plate in place. So, the force that is required to hold the plate in its place. Now, we are going to solve this problem using two different control volumes. The objective of using two different control volumes is to demonstrate that the choice of control volume is important. If you choose a correct control volume or if you choose control volume judiciously, then the effort becomes less. Okay. So, the first control volume that we have chosen is as shown by the dotted line here. So, this is our control volume. Now, we can write down the momentum conservation equation. We need to find the horizontal force. So, we need to write the momentum conservation equation only along the x direction. The liquid is being distributed in the vertical direction, but because the horizontal force is a part in the momentum conservation equation along the x direction. So, we will solve the equation along the x direction only. Okay. So, we have chosen the control volume, and now we will apply the momentum conservation equation. Of course, we will assume the flow to be steady and it is flow of water. So, it is an incompressible flow. The force that can have surface forces and body forces, but there is no body force along the x direction. So, this body force will eventually be 0, the flow is steady. So, this term will be 0. Now, when we do that, both these terms are 0 and the flow is uniform. So, we can replace this integral with a summation, and the problem simplifies a bit. So, we write f as x because there is no body force. So, the surface force along the x direction, that is equal to on replacing the integral with summation, you have u rho v dot a. So, v dot a is a scalar quantity and u is the x component of velocity. Now, if we simplify this, then u is x component of velocity, and x component of velocity, the flow is along x direction, and on in this control volume, the flow comes in with velocity u. There is only one surface on this control surface at the x plane where you have the non-zero velocity in the u direction. At two places, at these two places, the x component of velocity is 0, x component of velocity is 0. Of course, there will be a v component which is not 0 in both these places, but we are not considering v component of velocity. So, we do not need to find this out. Now, if we replace it in place of u, we write down capital U. So, that is x component of velocity. We need to find v dot a, and the area vector at this point will be pointing outward. So, we will have u into the jet area. So, that will be minus u a. So, v dot a becomes minus u a. So, f s x is equal to minus rho u squared a, right. Now, this is the total force along the x direction, and this force will be equal to, if we take the control volume and think about the forces that act on this control volume. So, we have a diagram showing the forces along the x direction on this. On this surface, the x plane, the pressure will be acting on the left surface, that will be equal to the atmospheric pressure multiplied by the area of the plate, because this area is equal to the plate area. Now, when the water jet hits the plate here, a reaction force will also be applied on the water. So, so in this control volume, the force on this side will be the reaction force from the plate. So, there are two forces, the pressure force on the left surface and the reaction force from the plate. Okay. So, we can write down f s x is equal to the force due to pressure. So, P atmospheric into area of plate, and which acts in the positive x direction, and the reaction force which is acting in the negative x direction. Remember that this is the x direction, positive x direction that we have chosen. So, from this we can find, or we can rearrange, write down f s x is equal to minus rho u squared a. So, P atmospheric multiplied by A p, which is pressure force on the left surface, minus reaction force by the plate on the control volume, that will be equal to f s x, which is equal to minus rho u squared a. So, now if we rearrange and find what is R x plate, the reaction force on the plate, that will be equal to rho u squared plus P atmospheric A p, but this is the reaction force that the plate applies on the control volume. And remember, what we need to find is the horizontal force that is needed to hold the plate in its place. So, we have not found the horizontal force yet. Okay. So, now what we need to do is we can do the force balance on this plate itself and find out the horizontal force. So, because the plate has to be held stationary, so the forces to all the forces will balance, so that the plate is in equilibrium. So, we will apply the force balance on this plate. Now, if we look at the plate, there will be a reaction, equal and opposite reaction force on the plate in the positive x direction. Then there will be a force due to atmospheric pressure in the entire plate surface area, okay, in the entire. So, you can consider this area and this area, but ultimately this will be the plate area. So, P atmospheric into A p will be the force because in the negative x direction, because of the atmospheric pressure or the surrounding air, and the horizontal force that you will need to put additionally to hold the plate stationary. So, when we write down this balance, we can write the Rx plate, the reaction force that is being applied on the plate in the positive x direction, minus pressure force P atmospheric A P in the negative x direction, and the horizontal force which is in the negative x direction. So, from this we can write an expression rearranging and find the expression for horizontal force. So, horizontal force goes on this side, and we find that F horizontal is equal to Rx plate minus P atmosphere into AP. Now, we can substitute the value of Rx plate which we find on the found on the previous slide. So, Rx plate is equal to rho u squared A plus P atmospheric AP, and we can substitute this here. P atmospheric AP, that will cancel out, and we get F horizontal is equal to rho u squared A. So, we have been able to find we are able to find the horizontal force that is required to hold the plate stationary. Now, we can choose a different control volume and try to solve problem again. So, this time we choose a control volume which surrounds the jet as well as the plate. Now, if we see here that in this control volume the horizontal force acts on the control volume itself, and the flow is coming inside the control volume. So, if we do this, if we apply the momentum conservation in this control volume and write down the equations. So, first let us look all the surface forces, because the body force again will be negligible. So, the surface forces on the two sides. So, from the left side there will be atmospheric pressure P atmospheric multiplied by plate area, and from the other side also you will have P atmospheric, and this will be multiplied by area. So, you have P ATM AP, pressure force on left side, pressure force on the right side, they will cancel out, and the horizontal force, the reaction force does not come in picture here. So, you have the net force in the x direction is equal to minus F horizontal. You can substitute in the momentum conservation equation. So, if you remember when we wrote down momentum conservation equation, the body force term was 0 and the unsteady term del by del T term was 0. So, this is summation over u rho v dot A. So, we replace Fsx is equal to minus F horizontal rho u, and this will be v dot A again minus u A. So, that minus F horizontal is equal to minus rho u square, and F horizontal is equal to rho u square. So, we can see by the choice of two different control volume, when we chose a control volume on which the force required was acting, we were able to solve the problem easily. We just needed to do or apply the momentum conservation equation only once. However, if we would have been asked that what is the reaction force on the plate or by the plate, then the first choice of control volume was appropriate. So, it depends on what is it that we are looking for, what is the force, what are the flow rates, that will determine the choice of control volume. Okay. So, let us look at the next problem. Now, in this problem we will consider a case where the control volume moves with a constant velocity. So, if we have a vane is generally a device which can turn the flow. So, this is the vane and a jet hits this vane, and the flow is, the direction of flow is turned from, so it comes along x direction, but then it turns at an angle theta from the horizontal, as we can see from this figure. and this vane is connected with the trolley. So, when the jet hits, there is momentum transfer, and because of the jet momentum, that momentum transfer, the trolley moves with a velocity v. The jet comes with a speed or a v, and it is aligned with the x direction when it approaches the vane. Okay. So, it moves under the influence of an impinging jet having an absolute speed v. What we need to find is the resultant force and the power that vane could produce. Now, we assume that the vane moves along the x direction and the direction normal to it is y direction. When this trolley moves with a velocity u, so there will be a reaction force, and we assume that the components of this reaction force are r x and r y along the x and y directions respectively. Okay. So, we choose a first thing we need to choose a control volume. So, we choose the control volume in such a manner that the control surface at point 1 is normal to the jet and control surface at point 2 is normal to the jet, and that may make our life a bit easier. And we also assume that the control volume move with a constant velocity u, because in this case the vane moves with the velocity u. So, if we consider that our control volume also moves with a velocity u, then it will be easier for us to apply the momentum conservation equation. And when we are sitting on vane moving with a velocity u, so the flow becomes steady with respect to the vane. So, let us look at the problem, and the jet area, it is also assumed the jet area at section 1 and section 2. So, section 1 where it is coming in the control volume, section 2 at both the places the jet area remains same. Okay. And the flow is incompressible and the velocity is uniform. So, first thing, because before finding out the force we need to find the velocities. We know the velocity at 1, but we do not know the velocity at 2. We know the speed because the area is going to remain same. So, v dot a will be same, but let us see. So, first apply the mass conservation principle on this vane. The flow is steady. So, the first term becomes 0. Now, when we apply this, the flow is uniform. So, the integral sign can be replaced by the summation sign, and we will have rho v dot a, that will be equal to at section 1 minus, because the flow is coming in, v and a will be in the opposite direction. So, minus rho v 1 a 1 plus rho v 2 a 2 at the exit. Now, we need to substitute the values of v 1 and v 2 and a 1 and a 2. A 1 and a 2 are same. So, they will be equal to a 1 and a 2. So, v 1 is equal to v 2, which will be equal to v minus u. Remember that this v is the velocity with respect to the velocity that is with respect to the control volume. So, v 1 is equal to v minus u. Okay. So, v 1 and v 2 they are equal to v minus u, and a 1 is equal to a 2 is equal to a, which is area of the jet. So, from this we can find the velocity vector at section 1, which is v 1 is equal to v minus u I plus there is no y component. So, 0 j. At v 2 the flow is directed at an angle. The magnitude of this or the speed is v minus u. So, its x component will be v minus u cos theta I, and the y component will be v minus u sin theta. And so, when we write it in vector form, v minus u cos theta I plus v minus u sin theta j. Okay. So, we have been able to find the vectors v 1 and v 2, which are the velocity vectors with respect to at section 1 and section 2. These are the velocity vectors or the velocity of the jet with respect to this control volume, which is moving with vane with the velocity or with the constant velocity u. Now, we can apply the momentum conservation equation to find out the velocity components or the force on the vane. Okay. So, let us write down the momentum conservation equation. F is equal to F s plus F v, the forces surface and body forces, the transient term plus integral over the control surface. Remember that the velocities here v, x, y, z, they are velocities with respect to a frame of reference which is moving with the control volume. So, even though what we have shown here this x, y here, but this is moving with a control volume attached with this control volume, the coordinate frame. Okay. Along the x direction, there is no body force. So, we can neglect the body force when we consider the force balance along the x direction. So, F x will be equal to the force on this control volume will be along the x direction is R x. The pressure forces from all sides, so from the left and right, because they are all open to atmosphere. So, atmospheric pressure and the pressure forces will cancel out, and that is the reason we have not considered the pressure forces here. Okay. So, F x we substitute R x. Now, this term we will have summation, and we need to write down v x component of velocity into rho v vector x y z dot d a or dot a. So, at section 1, the x component of velocity is v minus u into rho, and v dot a is minus v 1 a 1. X section 2, the x component of velocity is v minus u cos theta into rho and multiplied by v 2 a 2. So, we substitute the values minus, we can bring out at the first place minus v minus u into rho v minus u into a. Now, this will be v minus u cos theta rho, and v 2 dot a 2 will be again v minus u a. Okay. So, we need to see here that the difference that comes v minus u cos theta is the x component of velocity, and this will be v 2 a 2. So, that will be v minus u a. Okay. So, we will have that giving us rho v minus u squared a, which will be common in both this. So, we will take this outside the bracket rho v minus u squared within a bracket minus 1 from the first term, plus this will also have rho v minus u squared a. So, the only thing left is cos theta. So, R x will be equal to rho a v minus u squared into within bracket minus 1 plus cos theta, that is the reaction force. Now, we have been able to find the reaction force in x direction. What we need to find the reaction force in the y direction. Now, we do not neglect, let us do not neglect the mass of the vane, which is m. So, we do not neglect this n here m here, we do consider F b, the flow is steady. So, along y direction if we write, we have F y is equal to R y minus m g. So, R y is the force, the reaction force, and because of the mass there will be a force m g acting in the downward direction. Okay. So, R y minus m g, which is the force along the y direction. Now, there is no velocity at section 1 along the y direction. So, v component of velocity along the y direction is 0. So, the first term at section 1 is 0 for the momentum flow. The second term will give the v component of velocity at section 2 is v minus u sin theta, flow is going out. So, we will have v 2 a 2, which will be v minus u into a and rho. So, we will have r y minus m g or is equal to rho a v minus u squared sin theta, and we can take m g on the other side. So, we will have an expression for r y. Now, we know r x and r y, and that will give us the force that will be exerted by the vane. So, that is the reaction force, and the force that the vane will exert will be equal to this, but it will be in the opposite direction. Now, we need to also find the power that will be produced by vane. So, power will be generated because the displacement is along the x direction only. So, power will be generated only because of the x component of force. So, that will be equal to the x component of force into u, and this minus sign represents that it will be equal to minus r x, because the force is acting in the opposite direction. So, we substitute the value of r x, which is rho a u rho a into v minus u squared into 1 minus cos theta when you take minus sign inside. So, this minus 1 plus cos theta becomes 1 minus cos theta, and this is multiplied by u here. Okay. So, that is the power. Okay. So, we have looked at quite a few examples in the moment conservation equation, and it is important to solve different problems so that you get a feel of the problems, you get to see the choice of control volume or the problems that one encounters. So, I suggest that you should solve as many as possible as many problems as possible from different sources. Okay. Thank you.